Today we consider a classic mathematical puzzle, finding a number x that solves a polynomial equation. Sounds simple enough, right? Or is it? Let's test our intuition with a few examples. Can you solve x plus 1 equals 0 using only the natural numbers? How about 2x plus 1 equals 0 in the integers? What about x squared minus 2 equals 0 in the rationals? And finally, x squared plus 1 equals 0 in the reals. Take a moment to think it through and share your verdict in the comments. Dun 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 dun. Surprisingly, or maybe not, none of these equations have solutions within their respective number systems. But mathematicians don't see this as a dead end. It's an invitation to think bigger. When equations defy their number systems, we simply expand the rules of the game. We move from naturals to integers, from integers to rationals, from rationals to reals, and finally to the complex numbers. And when we reach the complex numbers, something extraordinary happens. The journey ends. The fundamental theorem of algebra guarantees that any polynomial with complex coefficients has at least one solution. With the question of existence resolved, we pivot to a deeper challenge. How can we find these solutions? The search for a general formula. For polynomials of degree 2, the well-known quadratic formula provides us with a solution by radicals. That is, an elegant formula using only addition, subtraction, multiplication, division, and the square roots. With some effort, mathematicians extended this approach to cubic and quartic equations. But when they turned their sights to the quintic, that mischievous equation had other plans. In fact, the quintic refused to play along, and after centuries of attempts, Évariste Galois and others in the early 19th century proved something shocking. There is no general formula to solve quintic equations by radicals. Why this is not a failure? At first, this might feel like a defeat, but in mathematics, impossibility often paves the way for discovery. The quest for a solution by radicals gave rise to something even more profound, Galois theory, a revolutionary framework that forever changed our understanding of algebra and symmetry. The takeaway? If a problem drives you to despair, keep in mind that mathematics always rewards you, even if the treasure isn't the one you were set out to find. A surprising twist. Here is a thought. Why can we solve quartic equations by radicals, but not quintic ones? What makes quintics so stubborn? To understand this, let's borrow an idea from a simpler impossibility proof, the classic mutilated chessboard puzzle. Imagine a standard 8x8 chessboard with two opposite corners removed. Can you cover the remaining 62 squares with 31 dominoes, each of which covers two adjacent squares? At first glance, you might be tempted to try different arrangements, but instead of brute force, let's rely on a clever idea: an invariant. Each domino covers one light square and one dark square. So, for a complete covering, the number of uncovered light squares must equal the number of uncovered dark squares. But on the mutilated chessboard, there's an imbalance. Two extra light squares. This imbalance makes it impossible to cover all the squares. The invariant behind quintic equations. The impossibility of solving quintic equations by radicals follows a similar principle. There's an invariant, a mathematical property preserved by all operations involving radicals. For some quintic polynomials, this invariant breaks, proving that solutions by radicals simply cannot exist. Unlike the chessboard puzzle, though, uncovering this invariant isn't simple. It requires a deeper look at number systems and the smallest fields in which equations can be solved. And here lies the genius of Galois theory. It bridges the gap between a polynomial's solutions and its coefficients, revealing the hidden symmetries that govern their behavior. Where do we go from here? Can Galois theory be explained in just 5 minutes? Maybe, but at the Academy of Useless Ideas, we are far more captivated by the twists and turns of the journey than the final destination. Today we've scratched the surface, laying the groundwork to explore number system extensions, invariants, and the revolutionary framework of Galois theory. In future videos, we'll delve deeper into these ideas and uncover the profound ways they've reshaped mathematics. For now, take this with you. Mathematics, much like a great story, isn't about tying up every loose end. It's about the lingering mysteries, the spark of curiosity, and the thrill of discovery. So stay curious, keep questioning, and join us for the next chapter of this mathematical adventure.